Welcome. This video demonstrates the creation of a simple but typical RTU application using a MODICON M340 and DNP3 protocol. The demonstration is broken into three parts so that the level of detail can be expanded beyond other similar demonstrations of the Unity Pro companion tools. This is part 1. To create the RTU application, I will be using these three Unity Pro companion tools. Each is available for you to download at the Unity Pro Experts YouTube channel. The target system architecture for this solution is shown here, and the basis of this demonstration is the use of Ethernet radios. Within the target system architecture, here is how I will configure the data to be communicated between the M340 and Vijeo Citect. Data that is strictly for visualization will be polled or manually refreshed on demand. Data for alarms and trends will be unsolicited, also known as report by exception. Data for control and set point adjustment will be on demand. This communications configuration will minimize system bandwidth usage during normal operation. Having available bandwidth opens up other possible uses of the bandwidth, like video file transfers, but that is a subject for another demo. So, for this simple but typical RTU application, I will begin in Unity with my MODICON M340 and its BMXNOR module. I export the application to a ZEF file, and then I will use the DFB Manager to create some code to import into the Unity project. The DFB Manager created code will include M340 hardware addressed variables via drag and drop and auto-assigned DNP3 point addresses. This will conclude part 1. In part 2, the Unity project will be exported again and opened with the RTUconf tool, where I will create the DNP3 communications configuration and set the DNP3 point parameters to accomplish the minimized bandwidth usage. DNP3 point parameter purpose and settings will be presented in detail, and then the RTUconf.xml file will be created. Just a reminder, this is the file that is loaded into the M340 BMXNOR module. This will conclude part 2. Then, in part 3, I will use the Bldr app to put all of this into a Vijeo Citect project and finally demonstrate the working system. Unlike some of the other demo videos, I will not show the actual creation of every little item. In this video, I will expose more of the details that go into creating the working solution. So let me get started. I am in my Unity project with hardware configured. There is no code and no variables. The simple but typical RTU application is tank level monitoring with trending and alarming. Alarm set points will be able to be remotely set from the Vijeo Citect SCADA system. I will use a DFB level transmitter object to link Unity to Vijeo Citect. First, I will export the Unity project to a ZEF file. Now I launch the U2V DFB Mngr. The requirements for monitoring the tank level include scaling of the level transmitter signal to engineering units and comparison of the real-time level value against 5 alarm thresholds: high, 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 low, 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 and a high rate of change. So I will select a DFB that meets these requirements. Displayed is a bitmap image of the DFB template section, which includes the template section variables from the DFB project for the DFB LIT SA5 V1. Here are the template section variables, with substitution markers in the variable names and comments, _x and _y respectively. This DFB was built for use in systems using Vijeo Citect and M340 DNP3 systems. This can be identified by the content of the variable custom field. The VJC Bldr syntax is included, VJC, VJA, and VJT, and the RTUconf tool syntax is also included, @AI, @AO, @BI, and @BO. Now I will create an instance of the template section. The substitution strings for the substitution markers are defined. This DFB has public variables that require value assignments. This is indicated by the public variables tree node having the color red in this section and substitutions pane. Note the mouse over help in the DFB instance data pane. Assigning the public variable values is by double-clicking the items. Automatic continuation through the required assignments is initiated. The M340 analog inputs have a default range of 0 to 10,000, so 10,000 is used for the upper limit of the analog input. And the upper limit of the scaled value I will set for 24, and the engineering units as feet. I will use a category 1 for the high priority alarm category, and a category 2 for the normal priority alarm category. And lastly, the area will be set to area 1. This DFB instance is for a M340 with DNP3, so I will let the DNP3 point addresses be auto-assigned, and the analog input requires assignment to an I/O module channel, so I will continue with these settings. The exported ZEF Unity project file is selected and loaded. An analog module is selected, and the LIT analog input variable is assigned to an open channel. I am done here, and I will not be assigning any more I/O into the Unity project, so I unload the Unity project. I save the created DFB template section instance, and I can close the DFB Mngr Tool. Back in Unity, I import the DFB section instance. Here are the variables now in my project with the substitutions and parameters. Note the auto-assigned DNP3 point addresses. I will build, save, and export the project again for use with the RTUconf tool. This concludes part 1 of this demonstration. To continue with part 2, locate the video M340 BMXNOR RTUconf Tool demonstration part 2. This can be easily accomplished by searching on YouTube for RTUconf. Thank you for your interest and time. Subscribe to this channel to see more demonstrations of Unity Pro tools, tips, and tricks.